Nothing else. To learn clearly. Are you able to hear me?
Yes, sir.
Board is clear. Board is clear. Okay, let's do some numerical and then we'll see the properties. So in the last lecture, there's the multiplication of mathematics. So on that multiplication, we'll see one numerical which is from GW exam. Okay. Consider matrix A is 4, 6, minus 1, 3, 0, 2, and 1, minus 2, 5. Matrix B is 2, 4, 0, 1, minus 1, 2. And my matrix C is 3, 1, 2. And ED, the whole transpose delta C. One option to is C transpose into C into A into B transpose. Option number 3 is C transpose A into B. And 4 is A transpose into AB into B transpose into C. And which was the given product set with of the given product. Option A, exactly one is defined. Option B is 2 are defined. Option C is exactly 3 are defined. And option number D is all are defined. Can you guys solve this? He has given us 3 matrices and then he has given us 4 different things, 4 different products. And out of the 4 products, he is asking us, okay, one is defined, or 2 products are defined, or 3 products are defined, or all the products are defined. In this case, we are not going to physically solve all the matrices. Okay, then you are not going to complete, you are not able to complete, you are not asking the answer. And in exam, there are 20-30 questions, and if you want to solve each and every question, then you get only 2.5 minutes per question. So, but obviously, we are not going to physically solve all this. Okay, it's only asking us that which is defined, which is not defined. So, if you remember, I said when you can multiply to matrix. So, is multiplication possible or is it not possible? When all the four cases multiplication is possible, then we can write all of them. So we'll have to verify in which cases the multiplication is defined. That's it. Okay, or that is multiplication is possible. If you see matrix A is of the order 3 rows and 3 columns, 3 by 3. Matrix B is of the order how many rows are there? 1, 2 and 3. How many columns are there? 2. This is of the order 3 by 2. Matrix C is of the order 3 by 1. There are 3 rows, 1, 2 and 3 and there is only 1 column. So the order is 3 by 1. Okay. Now see the options and let us see which is defined and not defined. So the first is saying transpose of AB into C. So first we have to find out if AB is defined or not. So A is of the order 3 by 3 and B is of the order 3 by 3. So when is it defined? Remember, if number of rows, okay, of second is equal to number of columns of first. Right? Number of columns of the first matrix will be equal to number of columns. It is defined. And what will be the order of the product? This. So my matrix AB will have an order of 3 by 2. Okay, and then what we have written AB transpose. Okay, then transpose of this matrix. So when you transpose, what happens is rows is written as columns and columns is written as rows. And therefore, this 3 will become 2 will become here and 3 will become here. So rows become column, column become rows. So the order of the matrix, okay, AB, the whole transpose will be 2 by 3, 2 into 2. And then it's telling us to multiply it with 3. So let us multiply it with 3. What is the order of this 3 by 1? So when is the multiplication defined? If columns of first is equal to column of second. See it. Therefore, given matrix A transpose by 2. Okay, the whole transpose is utility of matrix of the order 2 by 1. Yes, this is defined. Okay, so the first option is defined. Now let's verify second. So C transpose into C. So C transpose. So C is having an order of 3 by 1. So C transpose will have the order of 1 by 3 because rows will become column, column will become row. Into matrix C. Order of the matrix C is 3 into 1. The number of rows, columns of rows should be equal to number of rows of the yes. So now this will have an order of C transpose into C. This matrix will have an order of 1:1 because what remains over here is 1 and this 1. So the order of this product will be 1:1. Next, AB transpose. So we have already found out the order of AB transpose. This. So if we multiply it with matrix AB, whose order is 2 by 3. Now number of columns of first should be equal to number of rows of the second, which is not. Here I am adding 1 and here I am adding 2. This is not defined. So the second is not defined. Let's see third. The third you have C transpose. So C transpose will have an order of 1 by 3 into AB. So AB will have an order which we have already found out over here. AB is having an order 3 by 2. So order of matrix AB is 3 by 2 So the number of columns of first should be equal to the number of rows of second. Yes, it is equal. So the resultant matrix is going to have an order this P transpose A into B. This matrix will have an order of 1 by 2. Okay, this is my 1 and this is my 2. So the resultant matrix will have the order of 1 by 2. So yes, third is also defined P transpose into AB. This is also defined. So up till now we have verified for 3 and for 3 we have got that 2 are defined, 1 is not defined. One more option is there. Let's see that also. So first is in A transpose into A. So first is A transpose. So order of the matrix A is 3 by 3. So A transpose will also have an order of 3 by 3. Now that matrix is getting multiplied by matrix AB. Okay. And we know the order of AB. The order of AB is also 3 by 2. Let me write over here 3 by 2. So number of columns of first should be equal to number of rows of first. So yes, it is equal. Here also 3 and here also 3. Okay. And the resulting matrix will have an order of this 3 by 2. So the given matrix, okay, A transpose into AB, okay, this will have an order of 3 by 2. Now this matrix E transpose into AB has been multiplied with matrix B transpose. Now B transpose will have an order. B matrix is having an order of 3 by 2. So when you do transpose, rows will become column, column will become rows. Therefore, the order will become 2 by 3. So the number of columns of first should be equal to number of rows of second. Yes, here also 2, here also 2. So the resultant matrix will have an order of 3 by 3. So this product A transpose into AB into B transpose will have an order of 3 by 3. This entire matrix is now getting multiplied with C, 5 by C, and the order of matrix C is 3 by 1. So this will be 3 by 1. The number of columns of first should be equal to number of rows of first. So yes, both are equal. Therefore, the resultant matrix will have order this. This is a 3 by 1, and therefore this is also defined. So what is our answer? 3 products are defined and 1 product is not defined. So answer will be option number C. So the answer to the given question is option number C, that 3 products are defined. Okay, is it clear? Everyone has understood? Clear? For everyone, is it clear? It has come in the year 2012. Okay, GMT, it has come in 2012. Okay, let's go for the next numerical. Instead of numerical, let me start with the properties and I start with the properties. Students, please join with the school email ID. Every time I will not be able to admit you if I am writing on the board, I will not be able to admit you. Others are able to hear me clearly. Others are able to hear me clearly. One student has said that my voice is not clear. Others are able to hear me clearly. Because many times if the network problem is there, then that person will not be able to hear it clearly. And if there is a network problem from my side, okay, then, but obviously everyone will not be able to hear it clearly. If only one student is saying that I cannot believe it, all are saying that I see that there is some problem from my end. Okay, then the one student is connected, the one is able to hear me, the other is not able to hear, which means there is an internet problem. So I hope everyone has understood. Okay, you don't have to physically solve these matrices. So, okay, he has only given you to confuse you. And if you start solving, then you will not be able to solve for the entire, so it will be more than half an hour. Okay. So we'll start with the numericals later on. First, we complete all the properties. In this chapter, there are many properties. If you want to solve your board exam numericals, you don't require more properties. Okay, but when you want to solve the numericals which are pertaining to your GWT, then all the numericals, 90% of the numericals will be somewhere related to your property. You will be able to solve if only if you remember or by heart all the properties. And there are more than 15 properties in this chapter. Okay, so we are going to first write the properties. I'll prove certain properties and certain properties you have to write at home. And then once all the properties are done, we'll start with the numericals. Okay. Before going to the first property, we'll see what is a null matrix. In the last class, the last two types of matrices which we saw was a symmetric matrix and a skew symmetric matrix. One more type of matrix, there is many more matrices, Hermitian matrix, skew Hermitian matrix, idempotent matrix, orthogonal matrix, involuntary matrix. There are many such matrices, only those which are of use for us that I am showing. So, what is the null matrix? The null matrix is also called as zero matrix. So, matrix where all the elements are zero. A matrix where all the elements are zero is called as a null matrix. For example, so all the elements of this matrix is zero, therefore this matrix A will be called as the null matrix. Now don't think why are we even defining sir if everything is zero, why it is even required. So it will be clear in this first property itself if A and B are two matrices and if the product of two matrices is zero, then it's not necessary for A to be zero or B to be zero or both to be zero. Okay, just remember you must have done your vectors with little bit of vectors in your project. So work done, it's not necessary that if my force is non-zero and my displacement is non-zero, okay, then also my work done can be zero. It's not necessary that my force should be zero or my displacement should be zero. Then only I can say that my work done is zero. Why? Because work done is given as factors into cos theta. So even if your theta is 90 degrees, then also your version will be 0. So that is, okay, in the case of the satellite and the moon revolving around the earth or the planets revolving around the sun, the work done over there is 0. But the motion is non-zero, which means displacement is non-zero. It is revolving only due to the gravitational force of the sun or the gravitational force of the earth in the mentioned example. Therefore, it's not necessary for anything to be 0, that if any of 1 is 0, then only it can be 0. So the same is getting satisfied in matrices also. If the product of two matrices is 0, it doesn't necessarily mean that one of the matrices should be 0. In normal algebra, it is. If you have 0 over here, then this is not going to give you 0. If you want here over 0, then either of this one has to be 0. Okay, if this is your A and if this is your T and your final answer is 0, then in normal algebra, either one of it should be 0, then only you are going to get 0, otherwise you are not going to get 0. This is in the normal algebra. We are talking about algebra of matrices. Okay, so it is similar to your vectors, that if two vectors are 0, it doesn't necessarily mean that either of the one vector was 0. And therefore, there we have defined, okay, a vector called as a 0 vector. So similarly, here we are defining a matrix called as the null matrix. Okay, so that is why the definition is required. So let's see one example where this particular thing is going to happen. Let me just prove it to you. If I take a matrix something like this, the matrix A is 0, 2, 0, 0, and my matrix B is 1, 2, 0, 0. Okay, I have this matrix, and let me find out the value of AB. Let me find out the value of BA. Let me first find out the value of BA. If I do D into A, that is after matrix B first and then matrix A. Next row of first matrix, column of second matrix. So 1 into 0 plus 2, first row in first column. So 1 into 0 plus 2 into 0. Then first row into second column. So 1 into 2 plus 2 into 0. Then second row into first column, that is 0 into 0 plus 0 into 0. Then second row into second column, that is 0 into 2 plus 0 into 0. So I get matrix BA as 0, 2, 0, and 0. Let me also find out product AB. So first row into first column, so 0 into 1 plus 2 into 0. Then first row into second column, so 0 into 2 plus 0 into 0. Then second row into first column, so 0 into 1 plus 0 into 0. Then second row into second column, 0 into 2 plus 0 into 0. So I will get matrix AB is equal to 0 into 0, so that is 0. This is also 0, this is also 0, this is also 0. So two properties together. Okay, again the second property I am writing itself here. If AB is equal to 0, it does not necessarily imply that BA is 0. So two properties together I have proved over here. In the first property I am saying that if AB is 0, then it doesn't mean that A is 0 or B is 0. Even if both are non-zero, I can have the product of two matrices is 0. In the second property I am saying that if A into B is 0, then it doesn't mean that B into A should also be 0. So that is what I proved over here. The first is I've taken a matrix A and I've taken a matrix B. Both are non-zero matrix and I'm multiplying A into B. I am getting A into B as 0. So the first gets satisfied. That is A is 0, it does not necessarily mean that okay, either of the matrix is 0. Even if both the matrices are non-zero, we can get a 0 matrix or a null matrix. The second is no. B gets 0 found out the value of the A and you can see that B, all the elements are not 0. It is a null matrix or a 0 matrix written only if all the elements of a matrix are 0. But here I am adding one element which is non-zero. Okay, and therefore this is not a null matrix or a 0 matrix. So if AB is a null matrix, it does not mean that BA should also be a null matrix. It may or may not be a null matrix. Similarly, if product of two matrices is 0, it does not mean that either of the matrices should be 0. Even if either of the matrices is non-zero, my product can be 0, which is proved over here. Okay, I hope it's clear. Next is very simple. You can say third property, which is actually we do in your algebra. If you multiply any number with 0, you always get a 0. So here also, if any matrix is multiplied with null matrix, if any matrix is multiplied with null matrix, then the product is 0. Okay, if any matrix is multiplied by a null matrix, then the product is 0. So let me take a matrix A as 1, 2, 3, 4, and let me take a matrix B as a null matrix. So what is a null matrix? Where all the elements are 0. So let me multiply this matrix. So 1 into 0 plus 2 into 0, first 2 into first column, first 2 into second column, again 1 into 0 plus 2 into 0. Then second row into first column, second row into second column. So 3 into 0 plus 4 into 0. Here also 3 into 0 plus 4 into 0. So you will get 0, 0, 0, 0. Like normal algebra, when you multiply, okay, any number with 0, you get 0. So similar as in the matrix, when you multiply any matrix with a null matrix, okay, then you get 0. So null matrix is like 0 in algebra. And identity matrix, which was written that way, which was denoted by I, is like 1 in algebra. So in normal algebra, we have 1, right? In normal algebra, we have 1. So if you multiply any number with 1, you get the same number. Okay, 5 into 1 will be 5 only, 10 into 1 will be 10 only, 100 into 1 will be 100 only. So you get the same number. So similarly, if you multiply any matrix with an identity matrix, you will get the same matrix. So the next property is, if you multiply any matrix with an identity matrix, you get the same matrix. Let me take this as so first go into first column, 1 into 1. Sorry, 1 0 0, right? So the identity matrix will be 1 0 0 1. So 1 into 1 plus 2 into 0. First go into the second column, 1 into 0 plus 2 into 1. then second row into first column, 3 into 1 plus 4 into 0, then second row into second column, 3 into 0 plus 4 into 1. So I'll get A into Y. So I get A into Y as 1 plus 0, that is 1, 0 plus 2, that is 2, 3 plus 0, that is 3, and 0 plus 4, that is 4. Okay, which is the same matrix. It is matrix A. Therefore, when you multiply any matrix, okay, so when you multiply any matrix with an identity matrix, you will always get the same matrix. Therefore, one of your algebra corresponds to identity matrix in matrices, and 0 in your algebra corresponds to the null matrix in the matrices. So, hope it's clear. If you are starting in this manner, it will become easy for you to remember. Okay, let's see some more properties. So we have seen these 4 properties. Next property. So these are properties of transpose of a matrix. I will prove some and others you will have to prove it. So the next property is A transpose of whole transpose is the same matrix. If you take transpose of a transpose, you get the same matrix. Then the next property is A plus B the whole transpose is nothing but A transpose plus B transpose. Then next is A into B, the whole transpose will be B transpose into A transpose. Next, you can apply the similar property, you can extend it as A into B into T transpose can be written as C transpose into B transpose into A transpose. 9. Any constant into matrix the whole transpose will be nothing but equal to K into A transpose, where K is any scalar, that is any constant or any number. So I will prove some of the properties, others you will have to do it. So property number 5, let me take a matrix something like this: 1, 2, 3, 4, 5, 6, 7, 8, 9. So if I take transpose of a matrix, so rows will become column, column will become rows. So row 1 to 3 will become column 1 to 3. Row 4, 5, 6 will become column 4, 5, 6, and row 7, 8, 9 will become column 7, 8, 9. So this is my transpose. Now I have to take transpose of a transpose. So I will have to again take a transpose of it. So transpose means interchange rows with columns. So this rows will again become column. So row 1, 4, 7 will become column 1, 4, 7. Row 2, 5, 8 will become column 2, 5, 8. Row 3, 6, 9 will become column 3, 6, 9. Is it exactly the same as matrix A? Yes. Okay, therefore this proves transpose of a transpose will be with the same matrix. Okay, similar set you have complement, so it's the same set. Okay, so here you have the similar. Now here you don't have intersectional union, therefore addition is living addition only. Okay, otherwise there you have the similar thing. Only when it is union it becomes intersection, when it is intersection it is like union. Otherwise it's static. Here also it's like that only. Okay, let's prove this also A plus B. So let me take two matrices A as 1, 2, 3, 4 and matrix B as 5, 6, 7 and 8. So let me take LHS first. So matrix A plus B, so 1 plus 5 is 6, 6 plus 2 is 8, 7 plus 3 is 10, 4 plus 8 is 12. Therefore, my LHS, which is nothing but A plus B, the whole transpose. So rows will become column, column will become rows, the 6, 8 will become column, 10, 12 will also become a column. This is A plus B, the whole transpose. Now let's take RHS. So first I will have to find A transpose. So A transpose will become 1, 2, 3 and 4. And my B transpose will be 5, 6, 7 and 8. Rows become columns and columns become rows. Now let's add, let's take RHS. So my RHS is A complement, A transpose plus B transpose. So 1 plus 5 that will give me 6, 7 plus 3 that will give me 10, 6 plus 2 that will give me 8, 8 plus 4 that will give me 12. Is it same as your LHS? So LHS is also 6, 10, 8, 12. Your RHS is also 6, 10, 8, 12. Okay, therefore the second property also gets proved. Okay. Same we can prove for multiplication also. Let me write matrix B as 1, 2, 2, 1. Okay, so let's find out the value of AB. So first row into first column. So 1 into 1 plus 2 into 2. First row into second column. 1 into 2 plus 2 into 1. Second row into first column. 3 into 1 plus 4 into 2. Then second row into second column. 3 into 2 plus 4 into 1. Therefore, I will get matrix AB is equal to 1 plus 4 that is 5, 2 plus 2 that is 4, 3 plus 8 that is 11, 6 plus 4 that is 10. So, AB, the whole transpose will become 5, 4, 11, 10. So B transpose to A transpose. So first let's find out B transpose. So B transpose will be 1. This row will become column and this row will also become a column. Matrix A, so this row 1, 2 will become a column, 3, 4 will also become a column. So let's do B transpose. So first row into first column. Are you guys able to see the board? Okay. So first row into first column, so 1 into 1 plus 2 into 2. Then first row into second column, so 1 into 3 plus 2 into 3. Then second column. Are you guys able to hear me? Are you able to see the board? Okay. Okay, then let's solve this B transpose into A transpose. The second row into first column, the 2 into 1 plus 1 into 2. And second row into second column, the 2 into 3 plus 1 into 4. Okay. So I get B transpose into A transpose is equals to 1 plus 4 that is 5, 3 plus 8 that is 11, 2 plus 2 that is 4, 6 plus 4 that is 10. So is it exactly same? So this is my LHS and this is my RHS. AB the whole transpose and this is B transpose into A transpose. So our seventh property has also got true. You can try the property number 8 and property number 9 by yourself. Okay, if I keep on solving, then we'll not be able to go to the numericals. There are many much properties. Let's go to see. So let's first see trace of a matrix. First, let's see what do we call it as the trace of a matrix. So let me take this matrix of the order 3 by 2. Now trace of a matrix is defined only for a square matrix. Okay, why? Because a square matrix is going to have a diagonal. So sum of the diagonal elements is called as trace of an element. Sorry, trace of a matrix. So this trace of matrix A is nothing but sum of elements of diagonal. Sum of elements of diagonal, okay, are nothing but the trace of a matrix. In this case, the trace of matrix A will be nothing but 1 plus 5 plus 9. So that is 9 plus 6, that is 15. Okay, so trace is nothing but just add the elements of the principal diagonal. Okay, and whatever number you are getting, that is called as the trace of the matrix. So the next set of properties is for the trace of a matrix. So trace of a matrix K into A. A matrix which is K into A can be given as K times trace of matrix A. Next property, trace of matrix A plus B will be equal to trace of matrix A plus trace of matrix B. Next, trace of matrix A into B will be equal to trace of a matrix B into A. The product will not be same. So AB will not be equal to BA, but their trace will always be same. Okay. So let's see. Let's prove it. So I have a matrix A as 1, 2, 3, 4. So K times K. So let me take any K is nothing but any constant. Let me multiply it with any constant. Suppose I am writing 3A. So 3A will be 3, 6, 9 and 12. So trace of this will be nothing but trace of matrix 3A will be nothing but 12 plus 3, that is 15. And if I do trace of matrix A into K, so let's find out the trace of matrix A. So The trace of matrix A will be 1 plus 4, that is 5. And if I do k times, so what I have taken over 3. So 3 times the trace of matrix A is going to give me 3 into 5, that is 14. Hence the property gets proved. Okay, trace of K A matrix will be equal to K times the trace of A. Similarly, let me call it as matrix B. Okay, then A plus B. Let me add both these matrices. So 1 plus 3 will give me 4, 2 plus 6 will give me 8, 3 plus 9 will give me 12, and 4 plus 12 will give me 16. So trace of matrix A plus B will be 16 plus 4, that is 20. Trace of matrix A will be nothing but 4 plus 1, that is 5. Trace of matrix B will be nothing but 12 plus 3, that is 15. So trace of matrix A plus trace of matrix B will be 5 plus 15, which is 20. So again it gets proved. So trace of matrix A plus B will be equal to trace of A plus trace of B. Okay, it might look very simple to you guys. Okay, the properties are very simple and the proof is also very simple. But proof doesn't matter when it comes to the solving numericals. We don't remember the properties and we are not able to apply the properties. This is what happens. Okay. So remember this property. Similarly, you can try for third property also of the trace, that is trace of matrix AB will be equal to trace of matrix BA. You can try this property at home. I will prove certain properties and certain properties you will try, because there are a lot of properties in the entire chapter. Next, similarly, we have properties of trace of a matrix. We have properties for scalar multiplication also. And that is K times matrix of A plus B will be equal to Ka plus Kb. Next, K plus lambda, these are two scalars. Okay, one is K and one is lambda. Multiplied by matrix A will give me Ka plus lambda A. And property number 16, K into lambda into A will be equal to K into lambda A will be equal to lambda into Ka. So let's prove this property also. So again, let me take matrix A as 1, 2, 3, 4. A matrix B as 4, 5, 6, 7, 8. So matrix A plus B will be nothing but 1 plus 5, 6, 8, 10, and 12. Okay. Let me do 2 times A plus B. So this is my K in this case. I am taking K as 2. So I will get 12, 16, 20, 20. Okay. Let's find out the RHS K into A plus K into B. So my K is 2 in this case, so 2 into 8, so that will be 2, 4, 6, 8, and 2B, that will be 10, 12, 14, 16. So KA plus KB. So that will be 2A plus 2B. That will give me 2 plus 10, that is 12. 4 plus 12, that is 16. 6 plus 14, that is 20. And 8 plus 16, that is 24. Is it exactly same? So 2 times A plus B is equal to twice of A plus B. Okay, so this property also gets satisfied. Okay, one property I'll do it and one property you have to do it. So you do this property as an homework. Let me take K as 2 and let me take lambda as 3. Okay, so let us prove this. So K into lambda into A. So K into lambda, so K into lambda will give me 2 into 3, that is 6. So 6A, which is nothing but K into lambda into A. So 6A, that will be 6, 12, 18, 24. Now let's see, that also will be equal to K into lambda into A. So my lambda A will be nothing but 3A. So this will be 3 into 1, that is 3, this is 6, 9 and 12. Okay, then K into lambda A. So that will be nothing but 2 into 3. So that will become 2 into 3A. So I'll do 2 into 3A matrix. This is my 3A matrix. I'll multiply it by 2. So this will become 6, 12, 18, 24. This is exactly the same. Okay. So my next property also gets proved. So this is about the scalar multiplication. Though the properties may look very simple to you guys, but when it comes to the numerical solving, you are not able to remember it. So please keep on by hearting also the properties as I keep on writing the properties over here. Note down the properties and by heart the properties also. Next, let's see next concept, power of matrices. There are many more properties. These are written the properties and there will be many more properties. Now next properties will be on certain properties of symmetric matrix and skew symmetric matrix. Then we'll have properties of inverse of matrix and then we will have properties of adjoint of matrix. So lot more properties are going to come. Before that we are going to see power of a matrix. This is very important. Though the things look very simple, but many times we make a mistake. A square B will be written as A into A. We very well know that. Well, we very well know that A cube can be written as A into A into A. That can be also written as A square into A. Right? So let's find out what is it in terms of matrices. So again I take the same matrix 1, 2, 3 and 4. So my matrix A square will be nothing but A into A. So I will multiply the matrix. So this will be 1, 2, 3, 4. And multiply it with the same matrix 1, 2, 3, 4. So I'll get matrix A square is equal to first row into first column. So 1 into 2 plus 2 into 3. Then first row into second column. So 1 into 2 plus 2 into 4. Then second row into first column. So 3 into 1 plus 4 into 3. Then second row into second column. So 3 into 2 plus 4 into 4. So you will get A square is equal to 6 plus 2, 8 2 plus 8, 10, 3 plus 12, 15, and 6 plus 16, 22. So this is the value of A square. So generally what happens is, suppose this matrix A is given and is told you to find out A square, what the students do is this mistake. This is wrong. When I tell you, you have to find out A square, you are not going to do square of all the elements. If I tell you to find out A cube, you are not going to do cube of all the elements. And this is what I wanted to prove. If I do this, then 1 square will be 1, 2 square will be 4, 3 square will be 9, and 4 square will be 16. If I do something like this, then I will get 1, 4, 9, and 16. So am I getting like this? See what the value of A square I've got. I've got the value of A square as 8, 10, 15, and 22, which is not the same. Therefore, okay, and therefore, A square is not like A square, you have to physically multiply two matrices. Okay, then if you want to find out B cube, then I will have to do A cube is equal to A square into 8. So I multiply this 8, 10, 15, 22. Okay, into 1, 2, 3, 4. So again I will have to physically multiply. So I get A cube is equal to first one into first column. So 8 into 1 plus 10 into 3. First row into second column. 8 into 2 plus 10 into 4. Then first row, second row into first column. So 15 into 1 plus 22 into 3. Then first, second row into second column. So 15 into 2 plus 22 into 4. So we get A cube is equal to 8 plus 30, 16 plus 40, 15 plus 66, 30 plus 88. So we get A cube as 38, 56, 81, and 118. If I do cube of all the elements, I am not going to get 1 cube will be 1, 2 cube will be 8, 3 cube will be 27, and 4 cube will be 64. So we are not coming anywhere near to this. And therefore, when it is A cube, you are not going to do this. You are not going to cube all the elements. If you do this, you are not going to get the answer. Okay, so this is what I wanted to show you. So the way in which we apply the rules of algebra for the powers. Okay, the powers get added, okay, or the powers get subtracted. So the same thing can be applied to the matrices also. You can apply the same thing to the matrix also. So here I have written A raised to 3 is A raised to 2 into 8. A raised to m into A raised to n, and you can write that A raised to m plus n. So the law of indices which we have seen for the algebra and the normal algebra can be applied for the matrix algebra. Okay, the powers will get added. So the laws of indices you can apply similarly what you have applied in the algebra, but you have to remember one thing: when you're doing squaring or cubing or something, you will not cube or square the element. Instead, we will have to physically multiply it. We will have to physically multiply it to get the answer. And nobody that comes to your mind, sir, how do you find out if it is A raised to 50, if it is A raised to 100? How are we going to find out such? So we are going to see such numericals, such kind of numericals have some here. Exams also GMT. So that kind of numericals also will see at that time we'll see how and which properties to apply and solve. Okay. Let's write next set of properties. So we had written some 15 properties before, and now we are going to next set of properties. So these properties are for symmetric and skew-symmetric matrix. Okay. For symmetric and skew-symmetric matrices. So the properties, 15 properties which we had written were for the square matrices. For any square matrices, we can apply those properties. But this property what we are going to see can be applied only when a matrix is a skew-symmetric matrix or a symmetric matrix. For any other matrices, you cannot apply this property. The very first is, and this is very important, any matrix A can be represented as sum of symmetric and skew-symmetric matrix. And you can write it as I'll prove it, don't worry. You can write it as P by 2 plus Q by 2, where P is your symmetric matrix and Q is your skew-symmetric matrix. I'll prove it, don't worry. Next property, so if A is any square matrix, if A is any square matrix, then A plus A transpose gives the symmetric matrix and A minus A transpose gives skew-symmetric matrix. So therefore, you can write P as nothing but A plus A dash, and Q you can write it as A minus A dash. Let me prove it there. Then let's go to the next property. So suppose I have this matrix A. Okay. Can I write it as A plus A transpose minus A transpose plus A upon 2? I can write like this, right? A transpose will cancelled. A plus A will give me 2A divided by 2 will give me A. So in any case, I can write A as A plus A transpose minus A transpose upon 2, which I can write it as something like this. A plus A transpose by 2. And I can write it as plus, first I'm writing A and then I'm writing minus A transpose upon 2. Okay, I just separated 2. So I have written A plus A transpose by 2 plus A minus A transpose. And if I say that A plus A transpose is symmetric matrix, so let's prove it. So I have one unit square matrix 1, 2, 3, 4. So my A transpose will be 1, 2, 3, 4. Rows will become column, column will become rows. So if I add this to matrices, if I do A plus A transpose, so I get 1 plus 1, that is 2, 2 plus 3, that is 5, 3 plus 2, that is 5, 4 plus 4, that is 8. Okay, so this is my A plus A. So let me represent it as P. Okay, which I have done there also. So let me find out P transpose. So if I find out P transpose, this row 2 5 will be written as column 2 5, and this row 5 8 can be written as column 5 8. Is it exactly same as matrix P? You can see here the matrix P is also 2 5 5 8. My okay transpose of a matrix is also 2 5 5 8. And if A transpose is equal to A, then the matrix is called as the symmetric matrix. Here I have got same P transpose is equal to P. Therefore, the matrix P is called as symmetric matrix. And matrix P is nothing but what? A plus A transpose. And therefore, written over here that A plus A transpose will give me symmetric matrix and A minus A transpose will give me Q symmetric matrix. So let's find out A minus A transpose also. If I write A minus A transpose, then it will become 1 minus 1, that is 0, and 1, 2 minus 3, that is minus 1, 3 minus 2, that will be plus 1, 4 minus 4, that will be 0. And let me name this matrix as matrix. If I write Q, okay, then this row will become column to 0, minus 1 will become column 0. Okay, that will become. This is my Q dash, which is not exactly equal to Q, but suppose if I take from here, if I take minus sign common in matrix Q, take minus sign common, then 0 will remain as it is, minus will be plus 1 will be minus 1, 0 doesn't have sign, it will remain as it is. And you see, this is exactly the same. Instead of that, then I write as minus Q matrix. So therefore, I get Q dash is equal to minus Q. So we are saying that if A transpose is equal to minus A, then the matrix is called as Q symmetric matrix. So therefore, what I am getting in this matrix, which was nothing but A minus A transpose, is nothing but the Q symmetric matrix. So the second property also gets proved that A minus A transpose is the Q symmetric. So we know this is my Q symmetric, therefore I have written Q over here, and you know this is my symmetric matrix, and therefore I have written P over here. Therefore, this matrix A can be written as P upon 2 plus Q upon 2, where P is symmetric matrix, Q is Q symmetric matrix. And therefore, in the property 1, we have written that any square matrix can be represented as sum of symmetric matrix and Q symmetric matrix. Is it clear? Okay, I hope it's clear to you. Let's see the next property. let's see the next property. This is important one in the exam. Numerically is also there on this property. Matrix B transpose into A into B is symmetric or skew symmetric. Is symmetric or skew symmetric depending on whether A is symmetric or skew symmetric and B is any square matrix. B is any square matrix. So if I have a product something like this, it is only satisfied if the order is B transpose into A into B. If you change the order, then this property will not be satisfied. Okay, the order should be only B transpose into A into B. It should not be B into A into B transpose. Then the property may or may not get satisfied. In this case, the property will get satisfied. So B can be any square matrix, and A is if the A is symmetric matrix, then this product B transpose into A into B will be symmetric. And if your A is skew symmetric, then B transpose into A into B will be your skew symmetric matrix. Next important property, all positive integral multiples integral multiples of symmetric matrix is symmetric matrix. So if it is a symmetric matrix, and if you find out A square, A cube, A raised to 4, A raised to 5, you will get all the matrices to be symmetric only. Okay? All A square, A cube, all the powers are going to get symmetric matrix. But for a skew symmetric matrix, all positive odd integral multiples. Integral means integers and not fractions. So all positive odd integral multiples of skew symmetric matrix are skew symmetric. Whereas all positive even integral multiples are symmetric. So if it is a skew symmetric matrix, then the odd power will be skew symmetric, whereas the even power will be symmetric. Why? Because for skew symmetric matrix, A transpose is equal to minus A. So if it is odd power, it will remain minus. If you take even power, then minus will become plus and it will become symmetric. Okay, if you do square, then you will get minus A the whole square will be nothing but A square, which is symmetric. And if you take negative power, then minus A the whole cube will give you minus A cube. So therefore, it will remain skew symmetric. So for all the odd powers, the skew symmetric matrix will give you skew symmetric only as a product. But for all the even powers, okay, the skew symmetric matrix will give you a symmetric matrix. Okay. Next property. Next, if A and B are symmetric matrices, if A and B are symmetric matrices, then A into B transpose is symmetric if and only if AB is equal to BA. Okay. So if A and B are two symmetric matrices, so I am taking two matrices which are symmetric. Okay, and if I multiply, then we know the product is going to be symmetric only if, but that is if and only if my AB is equal to BA, because there I have written transpose. Okay, we know AB, the whole transpose is equal to B transpose into A transpose. Okay, and if my AB is not equal to BA, then I am not going to get A is equal to AB, and therefore this my AB, the whole transpose, will be symmetric if and only if my AB is equal to BA. Otherwise, even though matrix A and B are symmetric, okay, and if AB is not equal to BA, then my AB, the whole transpose, will not be symmetric. Instead, it may become Q symmetric. It may become Q symmetric. So we have done with the properties of symmetric matrices and Q symmetric matrices. Then we are going to see what do we mean by determinant of a matrix. Then we'll see what is adjoint of a matrix, what is inverse of a matrix. Because we have seen addition of two matrices, subtraction of two matrices, and multiplication of two matrices. But we haven't seen division of matrices. So that we will see it as inverse. Okay. And then we'll see those properties, and then we'll go with the numericals. And once, okay, all the important numericals of the chapter get over, and then we'll start with determinants chapter. So first we are going to concentrate on the matrices, we are going to complete the matrices, and then we'll start with the determinants chapter, and then we'll do determinant numericals also. So the next topic is determinant of a matrix or determinant of a matrix. So I have a matrix A, say 1, 2, 3, 4, 5, 6, 7, 8, 9. So the determinant of a matrix A can be represented something else. Delta A, or it can also be represented by this symbol and read as, and many times it also denoted by something like this. Delta suffix A or delta A or mod of A. All these are symbols and read as determinant of matrix A. Okay, determinant of matrix A. So let's see how to find out the determinant of a matrix. Please see and understand the procedure. And once we go with the determinant chapter, I can show you there are many different ways by which you can find out the determinant. But in this chapter and the matrices, I am going to show you only one method of finding out the determinant. But there are 4 or more methods by which you can find out determinant. Okay, I am going to show only one. This is required in this chapter. If I write determinant of matrix A, first I'm going to do with using expansion of rho Rn. You can do it with the expansion of rho 2. You can do it with expansion of rho 3. You can do it with expansion of column 1. You can do it with expansion of column 2 and expansion of column 3. But I am going to use throughout this chapter as expansion of rho 1. When we come into the chapter of determinant, I will show you the other methods also. Okay. But now we are not going to do a little bit complex, because here we are not only concerned with determinant. Determinant is only going to be the first step of the entire numerical. We will not waste a lot of time in finding out different ways of determinant. So when I am going to use this, as of now, you just remember the sign convention: plus, minus. I will tell you the reason also. Once we see this adjoint topic, I will tell you the reason also. As of now, you just remember this sign convention: first element positive, second negative, and third again positive. I will prove this sign convention, don't worry. The first element I write 1, and then again I will do something like this, and I will select the element. What I will do is, this element lies in first row and in first column. So I cancel first row and first column. So whichever elements are there, I will write. So this is 5, 6, 8, and 9. Then minus sign, the middle element I said should be given minus. The element is 2, so I will write 2. So now when I write the element 2, since it is in the second column, so this time I am going to cancel the second column. The element is in the first row and second column, so you have to cancel first row and second column and write all the other elements. So that is 4, then this is 6, then this is 7, and this is 9. Then the next element I said you have to write plus, so plus 3. So the element is in the first row and third column, so you should cancel first row and third column and write whatever elements are remaining. So that is 4, 5, 7, and 8. So write 4, 5, 7, and 8. Then first you have to go from right to left, and then you have to go from left to right in the direction of the arrows I am showing, and minus sign. So it will be something like this: 1 into 9 into 5, then minus 9, 8 into 6, minus 2 into, first you have to go in this direction, so 9 into 4, then minus 9, and then you will do 7 into 6, plus 3 into 6. First we go in the line, right to left, that is 9 into 4, then minus 9, then 5 into 4. So I will get 1 into 9 into 5, that is 45, minus 8 is 48, minus 2 into 36, minus 7 is 42, plus 3 into 36, 9 to the 36, 7 5 is 36. Okay, everyone has understood how to find out the determinant. Everyone has understood how to find out the determinant. First, you should always follow the direction which I have shown by blue line, and then by the yellow line. And in between both the terms, there should be minus signs. Okay. 45 minus 48 is minus 3 into 1, that will be minus 3. 6 minus 42 is minus 6. Minus 6 into 2, that will be minus 12. Minus minus will become plus. So this will be plus 12. And 36 minus 35, so that will be 1. So 1 into 3, that will be plus 2. Okay, so plus 3 minus 3 is cancelled, you get 12. You get determinant of A is equal to 12. So on basis of this, we have two more types of matrices, which we call it as singular matrix and non-singular matrix. So if determinant of a matrix is 0, then it is called as a singular matrix. And if determinant of a matrix is non-zero, then it is called as non-singular matrix. Okay, so if determinant of a matrix is 0, then it is called as a singular matrix. And if determinant of a matrix is non-zero, then it is called as non-singular matrix. So I hope you have understood what is determinant of a matrix. And you have also understood what is singular, non-singular matrix. Now let's move ahead and let's understand what is minors of a matrix. What are cofactors of a matrix? And what is adjoint of a matrix? So I have this matrix A as 1, 2, 3, 4, 5, 6, 7, 8, 9. Now minors are represented by Mij. Minors of a matrix. So how do you obtain minors? Just the procedure which I did right now. Okay, when I found determinant, what I did, the element, whichever element I took, I cancelled that row and that column, and then whatever value I got, that value will be called as minor. Okay, so if this is 1, then this is first row, first column, so the minor will be represented as n11. Here the minor will be represented as n12. The minor of this element will be represented as n13. The minor of this element will be represented as n32, and so on. Okay. So if I am representing a matrix by the minors, then it will be called as minors of a matrix. So let's try to find out what I mean by that. So when I say M11, so I cancel first row and I cancel first column. So whatever elements are remaining, that are like 5, 6, 8, and 9. M12. So when I M12, I will cancel first row and first column, second column, and whatever elements remain, I write 4, 6, 7, and 9. Then M13. So cut first row and third column, so whatever elements remain, that is 4, 5, 7, and 8. Then M21. So how many elements are there in this given matrix? There are 9. So there will be 9 matrices. Whatever number of elements are there, that many numbers of minors will be there. Okay. So in this case, 9 elements are there, so we have 9 minors. So M21. So you will cancel second row and first column. So you cancel second row and first column, what elements remain is 2, first row, M21, so second row and first column, so 2, 3, 8, and 9. M to 2. You will cancel second row and second column. So what remains is 1, 3, 7 and 9. M to 3. So when you write M to 3, you are able to cancel second row and third column. So what remains is 1, 2, 7 and 8. M31. So when I write M31, I am going to cancel third row and first column. First we always write row and then we always write column. So whichever row and column I have written, we will cancel it row and column. Okay? Well, cancel third row and the first column is what remains is 2, 3, 5 and 6. M32. Well, cancel third row and second column. So what remains is 1, 2, 3 and 6. Then M33. So you will cancel third row and third column. So what remains is 1, 2, 4 and 5. Then I have already told you what you will have to do. First, you should go in the direction of the blue line, and then it's in the direction of the yellow line, and thus minus sign in between the both. 9 into 5, 45 minus 48. Here, 36 minus 42. Here, 32 minus 35. Here, 18 minus 24. In this case, 9 minus 21. In this case, 8 minus 14. In this case, 12 minus 14. In this case, 6 minus 12. And then 5 minus 8. You get minus 3, minus 6, minus 3, minus 6, and then 20 minus 11, 20 minus 9. Minus 12, this will be minus 6, then this will be minus 3, minus 6, minus 3. So if I write minor matrix, then I will denote it by m. So this will be nothing but my m1, m1, 2, m2, 3. So I write all these elements over here. So my minor matrix, this will be minus 3, then you have minus 6, then you have minus 3, then you have minus 6, then you have minus 12, then minus 6, then minus 3, minus 6, minus 3. So this is minors of a matrix. Now, I hope you have understood what are minors of a matrix. You have understood what are minors of a matrix. Then let's see what is cofactor matrix. Cofactor. So cofactor will be nothing but you have to apply this sign convention which I have shown previously. Okay, plus, minus, plus, minus, plus, minus, then plus, minus, plus. So if you don't remember this signs, sir, how to buy this signs, you will get confused. It is as simple as that. The diagonals will have positive signs. Both the diagonals and both the diagonals write the positive sign, and in the remaining elements write the negative sign. Now, here this will be my M11, here M12, this will be M13, M21, M22, M23, M31, M32, this will be M33. So whatever minors we have found out, okay, we substitute all the values of these minors, okay, with this sign convention, then whatever matrix we get is called as the cofactor. Okay, so now first what we did, we have found out the minors of a matrix. Now, when you apply the sign convention like this, and then when you apply the sign convention to the minors, then that matrix will be called as nothing but cofactor matrix. Therefore, the cofactor matrix will be nothing but, okay, plus minus is minus, so this will be minus 3. Then here I have minus and this minus 6, minus minus will become plus, so this will be plus 6. Then plus minus is again minus, so this will be minus 3. Then this is minus minus will become plus, so this will become plus 6, plus minus is minus, so this will be minus 12. Minus minus is plus, so this will become plus 6. This will be minus 3, minus minus plus, so this will become plus 6, and this will be minus 3. Okay, so this is my cofactor matrix. Suppose if you don't want to by heart the signs also, then by definition we have cofactor is minus 1 raised to I plus j into Mij. So when I write M11, this is also 1, this is also 1, so 1 plus 1 is 2, minus 1 square, okay, will be plus 1, and therefore you have plus 1. When you write M12, so when you write M12, so this will be 1 plus 2, so that is 3, minus 1 this will 3 will be minus 1, and therefore you have minus over here. When you write M13, so this will be 1 plus 3, that is 4 minus 1 is 4 is positive, therefore here you have positive. Then here, when you write M21, so that will be 2 plus 1, that is again 3, so minus 1 raised to 3, that will be minus. So I hope this is how we find these signs for the cofactor matrix. But I have shown you a very easy method. Okay, first put positive signs in both the diagonals. Then whatever spaces remain, in all those spaces you put negative signs. Okay, then the matrix which you get is called as a cofactor matrix. Is that clear? Is that clear what is the cofactor matrix? So now let's go what is called as an adjoint matrix. Adjoint of a matrix. Okay, it is denoted by the symbol ADJ of A. So ADJ stands for adjoint of the matrix, and adjoint of a matrix is nothing but transpose of cofactor matrix. And that is why we have studied this also. So if you want to find out adjoint of a matrix, if you want to find out adjoint of a matrix, you have to do transpose of a cofactor. So if you want to do transpose of a cofactor matrix, you need minors of the matrix. Because cofactor is nothing but only sign convention when applied to the minor matrix, then the minor matrix will become a cofactor matrix. And when we take transpose of a cofactor matrix, we get which we call something as adjoint of a matrix. Okay? And therefore today we studied today how to find out minors of a matrix, cofactor of a matrix, then adjoint of a matrix. So adjoint of the given matrix which we have taken, okay, our matrix was 1, 2, 3, 4, 5, 6, 7, 8. And the cofactor of that matrix is this. So adjoint will be nothing but transpose of a cofactor. So adjoint of my given matrix which was 1, 2, 3, 4, 5, 6, 7, 8 will be transpose of this. So this row will become column. So minus 3, 6, minus 3 will become column. Then 6 minus 12 plus 6, 6 minus 12 plus 6. That will also become a column. Then minus 3, 6, minus 3. Okay? So this is my adjoint of matrix A. What was my matrix A? My matrix A was something like this. 1, 2, 3, 4, 5, 6, 7, 8, 9. So my matrix A was this. 1, 2, 3, 4, 5, 6, 7, 8. And I've got this adjoint. Okay, I've got this adjoint minus 3, 6, minus 3, 6 minus 12, 8, minus 3, 6, minus 3. Is it clear? Is it clear how to find out adjoint of a matrix? Next, let's define inverse of a matrix. Let's define what do we call it as inverse of a matrix. Inverse of matrix. Denoted by A raised to minus 1. So the same symbol is shown in the function chapter also. Okay. So what is inverse of a matrix is if I am able to define any matrix A and B. If there are two matrices A and B such that A into B is equal to B into A is equal to I, where I is our identity matrix. So AB is equal to BA at the same time, okay, their product is equal to identity matrix. Then the matrix B is called reciprocal of A. Or inverse of B. If I am saying that matrix B is called reciprocal of A, so but obviously 1 upon A is nothing but A inverse, or A raised to minus 1. So matrix B is nothing but reciprocal of A, which can be written as 1 by A can be written as A raised to minus 1, which we call it as inverse of the matrix. Therefore, from definition itself, we get one method of formula to find out inverse of a matrix, but this method, okay, is little bit, it comes in the board exams, but from the GW point of view, it is not suggested because they have to do a lot of transformation, which is still not seen. There is one more way to find out this matrix. It is A into B. A is nothing but B into N. I have denoted B as A inverse, so which can be directly written as A into A inverse is equal to A inverse into A is equal to I. So there is a one more method to find out inverse, and it is given as this. A inverse is equal to 1 upon determinant of A into adjoint of A. So there is one more simpler method to find out inverse of a matrix, and that is this formula. Okay, A inverse is equal to 1 upon determinant of A into adjoint of A. So now if you remember, few minutes back we had seen singular matrix and non-singular matrix. So, if I have a singular matrix, so for singular matrix my determinant is 0 for singular matrix. If I try to find out A inverse, what I'll get? I'll get 1 upon 0 into adjoint of A. Now what is 1 upon 0? Infinity, which is not defined. Therefore, if the given matrix is a singular matrix, when it will be called as a singular matrix if its determinant is 0. If the determinant of given matrix is 0, it will be called as a singular matrix. And if the given matrix is a singular matrix, then inverse of that matrix does not exist. So we have seen in relations and functions, just remember, the inverse of a function exists if and only if the given function is bisective. Otherwise, the inverse does not exist. Similar kind of a logic is here also. For all the matrices, the inverse will not exist. The inverse will exist if and only if my given matrix is a non-singular matrix. If the given matrix is a singular matrix, then my inverse of a matrix is not defined. Is that clear? I hope it's clear whatever we have done today. Today we started with one numerical wherein we understood, okay, how the orders of the matrices are important for multiplication. Then we saw many properties and we proved certain properties. Then we saw minus of a matrix, cofactor, adjoint and inverse of a matrix. And this point is very important. Okay. If the matrix, given matrix is a singular matrix, then its inverse is not defined. Okay. The inverse of any matrix will exist if and only if it is non-singular. So in the next lecture, we'll find out how to find out the inverse of a matrix, how to find out adjoint of a matrix, and then we'll directly start, we'll see some more properties of inverse and adjoint of a matrix, and we'll start with the numericals. Okay, all the previous years of numericals, we can come and later, AIEEE and DWE. Okay, so have a nice day ahead.